Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In previous videos, I told you that you could create your own tubular capacitor. I've made two of these to use in 14 megahertz traps that I created for a 20 meter, 40 meter inverted V for field day. And you know what? They worked great. I used the antenna with 100 watts and all is well. Then I started thinking, how could I improve them so that their voltage rating would work for higher power levels? It should be good up to maybe 20 kilovolts per the dielectric strength of the polypropylene I used as a dielectric. In this video, I'm going to show you how to build this improved version. You will be witnessing the first ever build of this improved version. If you have questions or comments, please feel free to comment on this video. If you find this video helpful, please click on the like and subscribe to the channel. Don't forget to subscribe. So let's go see what we need to do the job. So what am I going to need to build this capacitor? Well, I'll need a 5-inch length of 1/4 inch aluminum rod. That's 12.7 centimeters long and 0.635 centimeters outside diameter. We're also going to need a 4.5 inch length of 3/8 OD and 1/4 inch ID polypropylene tubing, which is 11.43 centimeters long, 0.925 centimeters OD, 0.635 centimeters ID. We're going to need a 5-inch length of 1/2 inch OD, 3/8 inch ID aluminum tubing, which is 12.7 centimeters long, 1.27 centimeters OD, and 0.9525 centimeters ID. We'll also need 1.5 inch long piece of shrink tubing, which has a 3:1 shrink ratio or better. It has to fit over the 1/2 inch tubing and shrink down to the 1/4 inch rod. One such piece of tubing can be found at DigiKey at the part number shown on the screen. We're also going to need two 440 by 1 inch screws. Now their actual length will depend on your particular application. And then we'll need the lock washers and nuts to go with them. The closest equivalent to that is an M3 by 2.5 centimeter screw with lock washers and nuts. We're going to need a hot glue gun or equivalent and, well, miscellaneous other stuff. So let's go get our materials ready. Everything needs to be measured and cut to length. So let's do just that according to what I already laid out. My aluminum rod is cut to 5 inches. My polypropylene tubing is cut to 4.5 inches. My aluminum tubing is cut to 5 inches. My shrink tubing is cut to 1.5 inches. And so now on to further raw material preparation. High voltage likes to use contaminating materials to build paths to arc across. And because we want to maximize the voltage rating of our capacitor, we want to clean our raw materials really well. No corrosion, no junk. As you can see, some of my stuff is pretty rough, especially this piece of 1/2 inch tubing. So first, I'm going to clean it up with some spray cleaner like 409. Then I'm going to wipe it down with acetone. And then finally, I'm going to put it in my drill press, rotate it as slowly as I can, and use some 600 grit sandpaper to get rid of the rest of the junk. And then I will wipe it down one more time with acetone to make sure it's good and clean. The inside of the tubing is going to be a bit more difficult. It'll be similar to cleaning a .38 caliber firearm. With all of this done, you can see my stuff is pretty spiffy. Well, things have to slide into place a certain way. So we're going to measure and mark everything while we wait for our hot glue gun to get up to temperature. From one end of the aluminum rod, we measure 4 1/4 inches and make a mark, and then another at 4 3/8 inches. From one end of the polypropylene tubing, we measure 4 inches and make a mark. Now, let's put it all together. The first step of assembly is to insert the aluminum rod into the polypropylene tubing about 1/4 inch away from the 4 1/4 inch mark. Put a bead of hot glue around the aluminum rod just ahead of the poly tubing, and then quickly push the aluminum rod into the tubing all the way to the 4 1/4 inch mark. Let everything cool so stuff doesn't move. Now, there should be a 1/4 inch deep empty cavity at the other end of the polypropylene tubing. Using the hot glue gun and starting deep into the cavity at the end of the polypropylene tubing, completely fill the cavity and then let it cool. The purpose for this is to deny a viable high voltage arc path between the end of the aluminum rod and the aluminum tubing, which surrounds the poly tubing. Once everything is cool, we insert the rod tubing assembly into the aluminum tubing to about 1/4 inch away from the 4 1/4 inch mark on the poly tubing. Put a bead of hot glue around the poly tubing, and then quickly push the aluminum tubing all the way to the 4 1/4 inch mark. Now we let everything cool. At this point in my first version, I used a 256 nylon screw through this whole assembly to keep things from moving relative to each other. And I'm trying to avoid this to prevent a possible path for high voltage arc through. I'm going to add some hot glue to the open end of the aluminum tubing to make the entire assembly more mechanically robust and to improve the high voltage performance. We do not want to put too much in there. We do not want to have to drill through it when we drill our holes. The next step is to drill the holes for the 440 screws. These are through and through holes 1/2 inch away from the end of the aluminum tubing and the aluminum rod. These are the connections of our capacitor to the outside world. The close fit drill size for a 440 screw is a number 32 or 0.116 inch diameter drill bit. For the M3, it is a 3.2 millimeter drill bit. Be careful to make sure the two holes are aligned with each other and go straight through. The final assembly step is to put on the shrink tubing. The purpose of this is to prevent a high voltage arc path from the end of the aluminum tubing to the aluminum rod. Position the shrink tubing just short of the 4 3/8 inch mark on the aluminum rod. Put a bead of hot glue around the end of the poly tubing in the 1/8 inch area. Quickly position the shrink tubing to the 4 3/8 inch mark and shrink it in place while maintaining the position of the shrink tubing. The heat gun should also warm the hot glue so the end completely seals. Now we let everything cool to room temperature. Once everything is totally cooled to room temperature, we can install our screws. Now we're ready to see what the value of this capacitor is. All right, so we're all ready to measure the value of our new fancy schmancy homemade capacitor. What are we going to need to do that? Well, we're going to measure it using the nano VNA. We're going to need an SMA to SMA cable. This is the one that came with my nano VNA. We're going to need an SMA to N adapter. And then my test fixture here, which is an N connector with a couple of clips on it like this. And then because there is no way this is going to be able to connect to this, I have to add to the mix a pigtail cable, which I will use to connect up to my capacitor. And then we need standards. Well, my short standard is this little piece of wire which I put between the two clips. My load standard is this 50 ohm plus or minus 0.1% metal film resistor. And then the open standard is, well, open clips. All right, so let's put our test situation together here. To begin with, we're going to connect up to our VNA. And then we're going to connect the other end of our cable to our adapter. Then we're going to connect our adapter to our test fixture. Now we're going to set this aside. We're going to connect our pigtail to the grounded side of this connector. And we want to make sure that we have a good solid connection there. I'm going to provide a little platform here so that the grounded ESD mat here is not going to interfere with the measurement at all. And then another platform for my capacitor to sit on when we do the measurement for exactly the same reason. Now we get to do our calibration. I'm going to make sure my clip is up here. So we have to open the application on the computer. So I'm going to open Nano VNA Saver. I'm going to connect to my device, which is on COM 7. Now I notice it just crashed. The way to fix that is this is the Nano VNA viewer. If you open the Nano VNA viewer and then go to the device, select your COM 7. In my case, notice I connected right away. Now, if I open Nano VNA Saver and connect to device, it connects right away. Now we had determined that we are going to evaluate this capacitor at 7 megahertz. So I'm going to set the start frequency to 6.9 meg and the stop frequency to 7.1 meg. I'm going to do a quick sweep just to kind of set that in place. Notice marker 2 here is already at 7 megahertz, so that's the one that I am going to be interested in. Now we need to calibrate. The thing is that we need to calibrate as close to where our capacitor is going to be connected as possible, and that's these points right here. So that is why we're going to use my fancy standards here in order to do the calibration, because then we can do it here and have good calibration because we're doing it right where the capacitor is at. Like I said, this is a non-ideal connection to our VNA. So we're going to do calibration. We're going to use the calibration assistant. We're going to say OK. And it says to please connect the short. And so we're going to take our calibrated piece of wire here. It's not calibrated. I'm going to stick it in my hot side of my connector here, which is the green one. I'm going to make sure that it has really, really good connection there. And then I'm going to take my clip around and I'm going to clip it on the end. Again, it's got a really good connection. I'm supporting it here. And we say, okay. And now it wants an open. So I'm going to connect this over here. I'm going to disconnect this here. And the reason why I do that is because that's about where it's going to be when we make our connection. We click on OK. And then we take our load, which is the next step. Again, we make sure that we have a really good connection to our load. And the same thing with our clip. And we click on OK. And we don't need two-port calibration, so we're going to click on Apply. And we're going to close this. Then we're going to do a quick sweep. And notice that it says 50 plus 61.5 milliohms. So that looks like a really good calibration there. But just to double check ourselves, we're going to disconnect our fancy standard here, put in our known 27 picofarad high precision NPO capacitor, do another scan, and it tells us that we have 27.309 picofarads. That is really good. So that tells me that this calibration looks really good. All right. Now comes the moment of truth. I'm connecting the hot side of our VNA to the center of our homemade capacitor. I'm connecting the grounded side to the outside of our homemade capacitor. See if I can get the whole thing in the picture there. There we go. Now let's see what it measures out to be. It tells us that we have 25.536 picofarad. Now it's telling us right now that we have a Q of 593.2. Now we would love to estimate the Q of the capacitor or believe what the nano VNA tells us about Q. But because of the construction of this capacitor, we expect the series resistance to be well under an ohm, and VNAs in general have trouble resolving this, even under the most ideal conditions. And our measurement conditions are far from ideal. So let me put the nano VNA on continuous sweep, and we can watch the reported Q, and you will see exactly what I mean by this. It's just all over the place. Now watch the Q. So you can see it is just all over the place, and this is the evidence that the VNAs in general have a hard time with these really low R values. If you look at the impedance over here, you'll see most of the time it's blank. So our homemade capacitor, according to this particular nano VNA at the time that we scanned it, has a value of 25.536 picofarads. And I've already measured it using my mini VNA Tiny, and that came out to 25.28 picofarads. And my high-end Tektronix VNA came out to 24.93 picofarads. So it's safe to say that this homemade capacitor has a value of about 25 picofarads. So why not use your antenna analyzer to measure the value of the capacitor? They say they can do this, and they do report capacitance and inductance values. But my personal experience so far with measuring capacitance and inductance and impedance using the average antenna analyzer has been pretty abysmal if you want any kind of accuracy at all. And I've tried a few of the various brands. Here's the evidence of this as I tried to measure the value of this capacitor using my recently factory calibrated MFJ 259C antenna analyzer. It won't even measure it at my target frequency of 7 megahertz. So I increased the frequency until it will read the capacitance, and it reports a capacitance value of 17 picofarads. Now, we already measured the value of this capacitor at 25 picofarads using 3 different VNAs. So this 17 picofarad reading is a shocking 32% off of the real value. Unfortunately, I do not have the means to test the voltage and current capability of this capacitor. I estimated that its voltage capability is on the order of 20 kilovolts based on the dielectric strength and thickness of the polypropylene dielectric, as well as the general mechanical assembly to maximize the creepage and clearance of the assembly. Now, I know its less capable cousin absolutely will work in a trap when using a 100-watt transmitter because, well, I've done that. If you have the means to test this assembly and can share your test results, I would be very interested in what you discover. If you found this video helpful, please click on the like and don't forget to subscribe. Thank you so much for watching. Until next time, Toodle-Oots.